So much is happening. At the same time, cars are being connected, a trend to go to electric vehicles, and at the same time trying to extend to more automotive safety as well as automated driving. And you can see how much the cars have transformed, for me, just even in the 10 years I've been involved in this. We started from an infotainment system with a single display that might have been at a high-end 720p. The cluster was pretty much a mechanical cluster with odometers. And now you see many of the cars that are coming out have many, many displays in the car. Might be 8 different displays being driven by one SoC. The resolutions are now much higher than Ultra HD. You can see here this would be a 55-inch wide display in the front. Things like rear view mirrors are being replaced with e-mirrors. And so you see this huge convergence of applications that might be entertainment applications coming from a broad ecosystem that you might see on a smartphone with an Android platform, together with hard real-time critical safety functions. And so it brings a lot of complexity into the software. And merging the worlds of the things that are there in adaptive AUTOSAR with other ecosystems like Android and Linux and those areas. So just a huge opportunity that comes with a lot of challenges that we have to solve together as an industry. So at Qualcomm, we've been involved in the automotive industry since about 2002, about the same time AUTOSAR was getting formed. Initially, it was in the telematics space. So we became deployed for the first time with telematics in the car in the GM OnStar starting in about 2002. It was about the same time Qualcomm was trying to establish CDMA as a worldwide standard for wireless connectivity. And so now, 20 years later, we have over 250 million cars on the road that have cellular technology. And we went from cars that had cellular connectivity being a niche to now well over 50% of the cars that are launched in the entire world have connectivity to the cloud built in through wireless technology. Things are always evolving. Over the last few years, 5G has been introduced at a much faster rate in the automotive market than 4G was. So a lot of needs in the market for that. And there's always something new. One of the things we're starting to look at now is bringing satellite connectivity into the car. So when you're in really remote areas that might not be covered by cellular technology, you've always got safety mechanisms that are available. About 10 years ago, Qualcomm decided to enter the compute space in automotive. And we did that by starting to offer products for infotainment. And we started that with our Snapdragon devices that were used in cell phones and modems. The reason that was interesting was because these are very high compute platforms that have a lot of the compute needs, especially high-end graphics, and multimedia, that were needed by those applications. Automotive has a lot of requirements beyond consumer commercial devices. So the first step was to really adapt those parts to meet AEC-Q 100 requirements for reliability, low DPPM in those areas. And we were successful in doing that. And now we're in our 4th generation of products in the infotainment space. I'll talk a little bit about what's happened in the course of that time. In 2019, we expanded into the ADAS market. And for ADAS, a lot more new things we had to bring beyond our consumer devices, because it wasn't just reliability, it was functional safety. And that meant bringing hardware changes into almost all of the IP blocks, as well as a lot of the structured approach that's needed in requirements management and the software development. So we're early in the journey on that, but having some pretty good success there. What I'll talk about in this talk is the trends first on the hardware, and then what that's going to mean for the software. And it's basically all of the themes that this group is working on. Now, one of the big focuses we have is what we call car to cloud, which is taking all 3 of those platforms that we have in the car and making them all connected to the cloud with an easy infrastructure that our customers can use. And that allows you to have basically real-time updates across those platforms and really adapt to the needs that we're seeing in the market. Let's see. As I mentioned, one of the reasons that we've been able to bring value in the space is really the complexity of the technology. If you look at an infotainment system or an ADAS system now, it's much more complex than needing just a single CPU and a microcontroller, or even a computer vision engine. You pretty much need all the IPs. You need graphics for rendering. You need accelerators for computer vision. You need programmable AI engines. You need connectivity with Wi-Fi, Bluetooth, cellular. And one of the strengths we have at Qualcomm is we have our own internally developed IPs across all of these areas. And it gives us the ability to highly optimize them for low power with very high performance. Initially, we were able to do well with leveraging a lot of these technologies, but then as we entered ADAS, we really had to start to bring new IP differentiation for areas that were very automotive specific. Things like bringing in a safety island to be able to do some of the controller functions. The AI requirements for this market are the most stringent in any application, because it's not just doing one piece of AI. It's many, many concurrent sensors, all that have to meet hard real-time requirements, and it has to run all the time. So you have to maintain that. Thermal management is really tricky with just how much performance is being packed into these devices. So those are all things that we continually need to be working on and solving together as an industry. This just goes through the journey. In 2016, we launched our first generation of cockpit programs with Audi and Honda. And there, we were mostly focused on the center stack. And the opportunity was that the center stack had evolved from being primarily audio functions to needing navigation and much higher levels of graphics performance. In the second generation, there was a desire in the industry to start to drive what's been called the digital cockpit, where the cluster went from being primarily mechanical odometers to a full digital cluster. But the cluster had safety critical requirements where, for example, you should never drop a frame. And the telltales needed to have robustness with an ASIL-B safety concept. So initially, these were QM devices, but we did add some things into the hardware to make this possible. For example, our compositor in the display engine had a CRC generator that would allow you to create a CRC of the telltales. And at the time, we needed an external microcontroller because the checker that was done for that needed to have safety certification in the hardware. But that was pretty successful, and one of the things that started a need for in the market is you had this mix of safety-critical functionality for the cluster with non-safety software from Android for the infotainment. So it introduced the need to have hypervisors and multi-RTOS and multi-VM on a single device. So here, typically, a lot of these systems were QNX or Greenhills. Those hypervisors, which were safety certified, and then in parallel with that, we would have VMs, which would be a lot of the OEMs had done their software around Linux. So there might be a Linux VM. And then at the same time, they wanted to leverage the ecosystem from Android for some of the entertainment functions. So that led to another VM that was an Android VM. So a lot of complexity. These are all concepts at the time that there was a lot of talk about, but really hadn't been deployed at scale. And now pretty much all the systems that we work on with OEMs do this. So you can imagine how fast this has moved in just the course of less than 10 years. In 2020, we introduced our third generation. And for this generation was the first one that we actually had a higher level of ASIL. The second generation was QM. So we had ASIL-A added into this. And we started to integrate camera functionality. So in the way that things evolve in automotive is usually new functions get added as maybe a new ECU that's specific to a function. So at that time, you might have had a rear view camera, you had a surround view, but those were typically additional full ECUs with a lot of cost, so only a premium vehicle would have had that functionality. But with the high performance that we have in these SoC solutions, it became possible to integrate the surround view, the rear view camera, along with the integration that had already happened of the cluster with the infotainment display. And those devices that are going in that are more expensive than the ones that were being used before, but you're eliminating entire computer systems. So the net result was much lower cost to enable that functionality in a car. And that's what allows something to go from being a niche and only a high-end vehicle to pretty much making it into the mass volume tiers. Now we're in our 4th generation, and here we've added full ASIL B of D support to our SoCs, so a lot more optimization and customization for auto than our initial products. And here we have the full digital cockpit, but in addition to things like surround view and rear view camera, we do driver monitoring integrated into the infotainment. And now that we have ASIL B of D, the new thing that's happening here is it's very difficult to invest in these engines. You saw the number of IPs. There's graphics processors, AI, and all of those things have a lot of complexity in software. And it takes a lot of time to learn the tooling to be able to optimize for those functions. So it's very useful to our customers to be able to have a common architecture across these different domains. So what we can offer now is a common architecture that could be running the full digital cockpit, but that same family can also be used in an ADAS system for an L1, L2 type system. So a common investment. These are still separate blades or ECUs even in some cases, but it gives a lot of scale for development around those platforms. You can see there on the right that the hypervisor, and one of the first things we had to do in the Gen 2 is prove that the Android could crash and you would never drop a frame on the cluster. So, little by little, this is building with a lot more mixed criticality support that can be done reliably across these systems. One of the new trends on the hypervisors is a lot of desire to go to Linux-based environments. So one of the things that's happening now is looking at safe Linux, and that's an investment area that's coming in the market. The next new thing that we're doing is we've already been able to have a single chip that could do ADAS or cockpit. And this year we've introduced the concept we call Flex, which you could actually, in a low-tier system, have the ADAS L1, L2 functionality as well integrated into the same chip that's doing the cluster. So that would be another opportunity for cost savings. It adds even more criticality under the mixed criticality support for the hardware. And so a lot of complexity in the software there, a lot of work we need to do. These systems now can also integrate some of the microcontroller functions. So I mentioned things like the external microcontroller that would do the checking for the telltales. You might have the error management for ASIL. Now these chips have safety islands integrated that have ASIL D lockstep chips or processors in them. So pretty much everything is contained in the single device. On top of that, with this architecture, we have different products that can be cockpit only across low tier all the way to high, Flex, which would combine the two domains together, and then ADAS only versions that scale all the way from L1 up to L4, which combines SoCs with AI accelerators. So a big opportunity to consolidate the learning on the software and make it easier to move in the direction that the industry needs to go. On ADAS, this was a new area for us. In 2019, we started, the first program was GM Super Cruise, which launched last year. And so there it's our SoC, but all of the stack software is done by GM. And pretty compelling product that's resulted there. We knew that for some customers, a lot of the OEMs and tier ones are no longer wanting to invest in their own stack. And there's a lot of systems in the market that use solutions like from Mobileye that had full turnkey solutions. And very difficult to invest in that at the scale of productizing the perception worldwide. So we decided it was critical to have our own stack and be able to offer that integrated with the SoC. We worked with Veoneer, a tier one, that had an internal group that had a very good stack. That group spun out into Arriver, which was a group inside of Veoneer. And last year we acquired the Arriver team. And that's been pretty successful, and now we're in the process of offering these solutions that have the integrated camera perception stack. The third one is an example of the importance to collaborate across the industry. So in addition to that, we wanted to have a full solution for the full ADAS stack, the drive policy in areas that typically the OEMs have been the leaders in that, because there's a lot of tuning they have to do for the drive and the feel they want in their cars. So we established a collaboration with BMW. And BMW is someone we love working with. They're very visionary. I think you mentioned earlier they were part of establishing the AUTOSAR group. And one of the things we like about BMW is when they approach ADAS and automated driving, it's a safety-first concept, but very focused on enabling leading technologies with having safety as the priority. So there we're going to be collaborating. The first products will be introduced in model year 25. And a lot of work there. And with that, we have the ability to take that same stack to other OEMs and offer it as well as a solution. So with this, we're starting to get a lot more engaged with a lot of the stacks from AUTOSAR, AUTOSAR Adaptive, Classic AUTOSAR, typically because we were still using external microcontrollers for some of the functions. In the past, we weren't as engaged with that. But in the latest SoCs, those are all integrated. So every topic that's being discussed at this conference is things that are highly relevant for the platforms that we're building. So where is the industry going? You saw in the cockpit slide how there was this constant integration where things that were separate boxes got merged. The other trend that I'm sure has been discussed here is the move from all of these smaller distributed computing blocks that are spread throughout the body of the car to an architecture that would have the sensors still located where they need to be, because those have to be in a specific location in the car. But then instead of having the processing located at the sensor, you would basically have these zonal controllers that feed the data throughout the car and then put as much compute as possible in a central blocks. Now, why is that important? One of them is the economies of scale. Centralizing it creates fewer computers and you can save cost. But it's also important for other reasons. For example, in ADAS for L1, L2 systems, those were typically initially a front camera. And the front camera was typically with the sensor in the rearview mirror. That imposed a very strict requirement that you couldn't really have anything beyond passive cooling. And you pretty much had like a 5 to 8 watt limit on that. And that was fine when you had sub-VGA type inputs from the camera, and it was computer vision versus the latest high performance ML. But now, most of those cameras to meet the NCAP requirements for 25 have to go to 8 megapixel camera resolution. And the complexity of the algorithms is an order of magnitude higher than what was being done even a few years ago. So very difficult to constrain that to the power targets to be in the rearview mirror. And at the same time, if you have that functionality there with the sensor and you have high power, that thermal interaction creates challenges with the sensor as well. So that's one of the examples of what would be driving this from a requirement standpoint, above and beyond just the desire to have more centralized compute. The way this is looking right now, it would start with many of the systems that used to be in external boxes, like the cockpit and ADAS, now become part of one box, but many people are adopting blade architectures. So you would have a blade for ADAS, a blade for cockpit. It still gives a lot of flexibility because cockpit and ADAS, in this case, are both addressing the same sensors. So you want to be able to have that together. But it creates a lot of flexibility and scalability. So I mentioned the Flex. A low-end tier might have a single blade that does cockpit and ADAS together. I go to a higher-end system, it's going to want a full blade or a full chip just for the cockpit. You saw the size of the displays that we're talking about in some of these systems. That entire chip plus more is needed to handle the graphics requirements for high-end systems. And then for ADAS, as you go to L2 plus high-end systems, and maybe L3, you might need multiple blades for ADAS. But you want those to be able to collaborate very well together. And you might have a single blade that handles L2 plus, but when you go to L3, you want another blade that gives you the minimum risk maneuver and gives you redundancy that's needed to meet the safety requirements. So I think this type of architecture is trending and where a lot of the systems are going. And it's just going to continue to be fueled by higher and higher compute requirements that will come. And will keep driving a lot of advancements in the industry here. So then what does all this lead? You're going to central compute. Instead of having a bunch of computers that have single functions, now I have massive computers that are running huge concurrencies, mixed criticality combined with non-critical functions. It introduces a lot of complexity in the software and a lot of combination between domains. So we start with the central computer. On top of that, you have your BSP, your RTOS, and then we have the middleware. This is where adaptive AUTOSAR and classic AUTOSAR would fit. CarOS is an effort that a lot of the OEMs are doing to create an abstraction across different middlewares and across hardware platform. So you'll see a lot of the different OEMs have their version of something like a car.os. And then the goal is to start to enable all of the data from the sensors, a lot of the intelligence that's being mined in the car, to be able to be exposed to the cloud and offered as services. So you can imagine that there's a lot of interest in location data, for example. So if I had a car that was being used in a fleet, can I geo-fence it, for example? To do that, I wouldn't want to just sit there and send the location data up all the time. I might want to create it as a service and have a publisher-subscriber type model where that data could be exposed and then people could subscribe to it, but only be alerted if there was a specific event. And the event that they're interested in might be different by each application. So very important to have structured approaches to this. And I think that's a lot of the themes that the groups here are working on. The model of engagement on the software development has moved to agile. And most of these projects have many, many companies involved. So it's very complex. And a lot of times, the different companies are working together in a common repository and collaborating extremely in an agile way. So these are learning new ways of working for a lot of this. It's very different than how we did software years ago. And then if you move to the top layer, it's very important now to have the connection to the cloud, not just for the services, but it's also leading to a whole new need that a lot of these OEMs, for example, BMW in their ADAS stack development, we have the piece we're doing, which is a computer that's doing the drive policy and the camera perception. But they have many other systems involved. They've got a radar perception ECU. They have LiDAR functions they might add. They've got the interface to the MCUs that are doing the body control. So they want to be able to have a system that's in the cloud that has software from all of us, and they can run that as a software data factory that would let them automate regressions and testing. So in the past, a lot of that was done on premise with just kind of dedicated boards that were wired together, and that's still needed for like a hill environment. But you want to really be able to mirror all that software in the cloud and have a very agile way of flexing that. And when you need to regress, have very quick turnarounds that can maximize the huge amount of parallel compute in the cloud. But what happens is I want to run all this in a digital twin in the cloud. The cloud infrastructure for software is much more modular and service-oriented than the embedded software that's typically running on these SoCs. So it's been very complex to enable that vision where I take common software that could run in a hardware abstracted way on the embedded platform and at the same time run in the cloud. So those are all things I think right now we're trying to solve. And making the layers modular, you could say that the code should be very similar, but in the cloud I might have full dynamic orchestration. In the embedded platform, maybe I don't need that yet, but I need a static allocator that has some of the QoS mechanisms. And the services need to be exposed in ways that are very common. This is where we see some of the move to Linux, for example, because the cloud might be an enterprise Linux environment. So if I could have that same enterprise Linux in the car, that would be very powerful. Here's some of the themes, and I think these are all topics that the teams here are addressing. But what are some of the challenges for enabling SDV and the multi-domain consolidation? The first one is we see that, for example, in the systems we're in now with our safety island with the AP, we actually have classic AUTOSAR and adaptive AUTOSAR both running on the same platform. So how do I get those environments to run very seamlessly together and make that very efficient for developers? The second one is the standardization of all those additional layers for the software-oriented architecture. The services layer, which is really above where adaptive AUTOSAR and classic AUTOSAR have typically been. And how do we harmonize all of that? I think Thomas has talked about all the other groups that AUTOSAR is engaged with, the ones that maybe are coming more from the cloud in terms of how do I unify the cloud architecture with the embedded architecture. If I'm going to have this software run quickly, there's all kinds of critical libraries. A lot of those libraries in the past, like math libraries, the graphics libraries, they typically weren't safety ready. So how do I get that infrastructure in place? And then finally, the specs for the software layers are common, but if there's different tooling across vendors, then that's a challenge as well. So that could be another area that would be very interesting to harmonize over time. And you can see here I focused on ADAS and cockpit integration, but we have a lot of OEMs coming and saying, what's next? Could you start to integrate the body functions as well? And it's clear that that's possible. It's just a matter of time and continue to move forward down this journey. Here, this just talks about really the opportunity. If we can do this software-defined vehicle, it creates a huge amount of additional opportunity for the entire industry to create connected services. That can offer better experiences to the user, but it could also offer a lot more monetization opportunities to the OEMs and to the whole ecosystem. So how we manage data and make that available and mine it for productive use is going to be super important. And you can see here, as Thomas mentioned, a lot of this is focused initially on commercial vehicles, but these same concepts expand to fleets, they expand to two-wheelers, bikes. We're seeing a lot of interest in the solutions we have for automotive to go into those other industries as well. And you can imagine the opportunity, for example, for two-wheelers. I want to be able to know where the bikes are. I want to be able to geofence them. If I'm in San Diego, I want to be able to constrain that the bikes aren't running on the sidewalk and endangering pedestrians. These are all things that could be accomplished with some of these software ecosystems that we can build together. So finally, together, this is all about enabling the car for the future. There's a lot of progress that's been made, but there's many more adventures and opportunities ahead. The cars are already connected. We have quite a bit of low-level driver safety functionality, but autonomous driving is a journey that's going to be still decades to fully explore. And then as we do this, how do we make the car more fun to be in, richer media content experiences, more personalized? All of these are opportunities ahead for the things that we're doing, and really appreciate the chance to be here and talk about some of these things.